All right, welcome everyone. This is a short-ish video just to explain a little bit more about what I called Inada conditions. So this was something we discussed. And, you may not hear this, so I realized, and kind of digging around and where the term comes from, this is something that macroeconomists refer to a lot because it originally came out of a model of the macroeconomy, and specifically it relates to the production function. So the Inada conditions originally were about the marginal products going to infinity as one of the units of capital or labor went to zero. So to kind of guarantee a good profit maximization problem. So at any rate, that's not really what we're talking about. But in our case, the way that I had framed it would be to say that the limit as consumption goes to zero of the margin utility of consumption being equal to infinity. That was our key condition. And I want to kind of explain why that makes a difference, right? So if that's true, then what it means is that I know my consumption will always be strictly positive. And I think just kind of running through the intuition helps you understand why that is going to be the case. So if I'm going to go back to, let's say, my beer and pizza consumption, utility of beer and pizza, and it's subject to this constraint. That my total expenditures have to be less than or equal to my income, although we know now that that constraint on income is typically always going to bind. And then we can add in that these have to be positive. Now, let's suppose that the Inada condition is true, right? So if I took the marginal utility of beer consumption when beer is equal to zero, and that was equal to infinity, or it was getting very large, approaching infinity. And you do have to be careful here. This is math econ. So if I took log as my example, so that the margin utility is 1 over CB, notice it only approaches infinity as CB, we would write this, approaches zero from the right. So as CB is, starts positive and gets closer and closer to zero, but is always positive, then the margin utility is getting bigger and bigger. If CB is negative and coming to zero from the negative side, then obviously the margin utility is minus infinity. So the limit doesn't actually exist, but it exists as it approaches zero from the right. So that's what I'm referring to. It's a technical point there. Okay, so notice this margin utility, as C gets closer and closer to zero, keeps getting bigger and bigger and bigger. So let's say that CB was equal to zero. That was my best choice, right? So I had to consider the corner solution, let's say here. Well, if CB is equal to zero, notice, right? I can increase CB by a really small amount. I'll call it delta CB, where that's positive, but potentially very small. So what do I gain from that? Well, I gain my margin utility times that change. And the point here is that when that's true, that gain is going to be infinity, right? Or extremely large. Right? If C of B is equal to zero, I can just give myself a very tiny amount, right? One sip of beer, tiny sip. and my utility goes way up. The margin utility from that small SIP is so high that I get a huge gain. And notice, well, what's the cost? Well, if I want just a little bit of beer, I'm gonna have to pay for that with some pizza consumption, right? So I remember I have my budget. And if I'm going to increase this by a little bit, I have to decrease my pizza consumption by a little bit. And so whatever that amounts to, you could work it out. It's some change in CP. And so I lose margin utility of pizza consumption times CP. But notice, because CP is positive, that's some number that's definitely going to be less than this, right? So this is definitely less than infinity. And so I know that the gain is always much bigger than the cost. So if my Inada condition is satisfied, it implies that zero consumption is really bad, and I would never get anywhere close to that. The gains from correcting that are huge, and the costs are going to be finite. So that's kind of the main idea, right? So typically, we're always going to make this, if I'm just using a general utility function, U of CB and CP, I would always make the following assumptions. I would say that I would just write it in this way. Strictly increasing in both CB and CP, right? So U1 greater than 0 and U2 greater than 0, derivative with respect to the first and second argument. And then I would want it to be strictly concave, where we get into those conditions that we had before, that both double partials are positive. And then that third condition, right, that when I take the partial, so I've got to have those things minus the mixed partial squared greater than 0, right? My thing is jumping all over the place. And the other condition that we talked about previously. Okay, so as long as it's strictly concave and strictly increasing, I'm good. And then I'm also going to add the following condition, that the limit as C goes to 0 of U1 of C, we'll call it CB, is equal to infinity. The limit as CP goes to 0 of U2 equal to infinity. So these are my Inada conditions. Right, so I'm going to make all those assumptions, strictly increasing, strictly concave, and Inada conditions, and then I can solve the problem somewhat relaxed, knowing that I'm going to have what we call an interior solution. The consumptions will have to be strictly positive if all of these things are satisfied. So most of the time in this class, we're going to work with a specific utility function, but at least you have an idea here. Don't know what happened there. At least you have an idea of kind of what the intuition behind this is. So there's a lot there. Take from it what you can. And if you have more questions about these things, for sure, let me know.